Good afternoon. I'm Bill Kane. I am chair of the ARB Shading Language Work Group. I work for AMD. I get a chance to work with some great colleagues who also work at AMD. And because of the work in Khronos, I actually get to work with some great colleagues who don't work for AMD. That's one of the special things about this place. Today, I've been doing shading language stuff for a long time, and I think it's really, really cool stuff. I hope you all do too. So I have to go back and do a brief way back moment. And you didn't see my slides before. Yes, the cool thing for me with what's happening with the shading right now is we are no longer side effects free. And that is really kind of cool. Along with that, the significant extensions that are dealing directly with side effects and side effects free are ARB conservative depth, ARB shader image lodestar, and shader atomic counters. I'm going to give a few simple examples. One which I please don't end up putting this out in the wild. It's an example for teaching purposes only. Something old school and something new school. So the way back moment. 10 years ago, in a conference room just about like this, at a BOF just about like this, in the Wilshire Grand, at the Wilshire Room in LA at SIGGRAPH 2011, the idea of the GLSL was born and announced before we even really started working on it. And we all were struggling along with these assembly language, shading language program structures, which were just abominable to use. And the shading language proposal came in by the end of the year. We actually had courses prepared to go to a GDC and SIGGRAPH the following year, and it got put into a GL2 extensions for a while, kind of a version of X extensions, and then promoted into core in fairly short order. So just want to have to say kind of happy birthday to GLSL. It's been a decade. Also think about how widespread it's becoming. It's definitely been out there on the desktop for a long time now. GLSL ES version of it has been out there on handhelds, and now with WebGL it's popping up in your browsers as well. So it's pretty pervasive, and that's another significant accomplishment of this language. So I always look at things from the point of view of shader. So the way things were really side effect free and designed to be that way. You had a shader, it pulled in some stuff for inputs, it output some stuff. It had a limited, especially at first, limited number of read-write resources and temporaries. It could read from uniforms, which effectively think of uniforms as constants. They just happen to be API-provided constants. They could read from textures and think of textures as constants. They just have to be filtered constants. And other than that, the shader had no side effects of any kind. Every vertex could be processed completely independently of every other vertex. Every fragment could be processed completely independently of every other fragment. With one tiny exception. When you do implicit derivatives or explicit derivatives. For implicit derivatives from when you're doing texture fetches with MIP mapping or anisotropic filtering. Explicit derivatives are when you actually end up asking for a derivative in it. You need at least limited information of your neighboring text pixels that are in flight with you. But other than that, everything is embarrassingly parallel. So we're adding in the side effects. Oh, it has some interesting implications. For the first time, I'm giving you a big chunk of memory that you have read and write access to, random read and write access to. And if we did it wrong, we turn the embarrassingly parallel graphics pipeline into this wonderful serial syrupy mess. We haven't done that, thankfully. I'll explain some of the restrictions we have on the kinds of ways you can do images, loads and stores, and operations on them. And it makes it a little bit more difficult for you as a shader writer, but it makes your speed of the shaders that you write much, much, much faster as a result of those restrictions. So I'm going to focus in on the fragment level. These things generalize up all to the other levels of the pipeline. But it's an embarrassingly parallel world we live in. So there's a triangle. Think of this one. It happens to be a multi-sample triangle. The fragments in green are the fragments that have to be shaded while you try to rasterize this. The fragments in red are the ones that might be required for implicit or explicit derivatives. Those might be think of them as along for the ride just to provide you with those derivatives. They will not write to the frame buffer. And, coincidentally enough, they will not write to images either, even if you ask them to write to an image. So, the memory restrictions that we put into this thing. You can randomly write into this memory, and it will be written. I won't tell you when I'll write it, And I won't tell you in what order I'll write it, but sooner or later it will pop up in that memory. And I'm going to give you a set of controls to make sure that you get the memory there when the value's in the memory there when you need it. Unqualified essentially says, hey, I'm the only person playing with this. And when I say my fragment shader, my vertex shader, whatever shader I'm working at, this particular instance of this shader, I'm the only thing that's touching this particular memory location. Don't have to qualify it at all. If I'm going to use that in a subsequent pass, I might have to put a GL memory barrier in it to have that pop up in another part of the pipeline. But from my shader point of view, I don't say anything, I unqualify my memory, I'm good to go. However, let's say I have something like an atomic counter and an image buffer, and I know that I'm going to be writing it, but somebody else other than me might be reading it. I need to make that memory coherent. Otherwise, I might be reading and writing to a temporary cache location that's not cache coherent. So it's effectively saying, if I have a cache, it better be cache coherent. If I don't have a cache, give some mechanisms to make sure that I know that the memory finally ended up infinite time getting out there. Volatile is like coherent, but with one other addition. I'm telling you that you have to do every read and you have to do every write. Let's do a little contrived example. I read a value, I got the value, I write it right back to the same spot, and I read it back again. Now some compilers will assume, what an idiot! You could have done that once! And in fact, they'll do it for you that way. Volatile will keep the compiler from doing that, because how do I know when I got the value first, when not somebody else changed the value? And when I put it back the second time, somebody else might need to see that new value, which is now the old value, but you know what I'm saying. And then I get back, it still might be yet another value. So volatile is the one that says, I might be touching it, somebody else might be touching it. Please commit every read, every write to that memory location. Write only seems pretty obvious. I'm the only thing, my shader is only going to write to this image, and read only. I'm the only thing that's going to be reading to it. And then restrict is very much like the restrict on a C++ pointer. These handles for images are the only things that are going to be used for, in this shader, talking to that image. So I don't have to worry about aliasing. Each one of the individual handles will be talking to a distinct piece of memory. Finally, I use memory barriers. Remember, I said these things are out of order. The writes that I do and the reads that I do may or may not end up in the memory in the order that they were in the shader. A memory barrier inside the shader, though, says all of those things have had to have been completed prior to the rest of the reads and writes that you have in the shader. So if I have 4 reads up here and 4 writes up here, they go in any order, put a barrier in them, they all better be done before the next set of 4 writes in that shader take place. It's not saying anything at all about whether or not the fragment next to me has done anything. It's not even saying anything about whether or not the fragment next to me is running. It's just saying my shader has committed all those reads and writes prior to the rest. Built-in functions, the image load is exactly what you think it would do, just like what a regular traditional text will fetch. The image store is the new one. That's the one that says, please put the textile back into the image. We have a bunch of atomic functions. High level, all the atomic functions will fetch the textile, take the data that I passed into the function, perform an operation on it, put that new value to get into the textile, and return to my shader the original value of the textile. So the very first part of the process is pull the old textile out, do some new stuff, put the new textile in, but I get back in the shader the old textile. The only one other than that, all the adds, mins, maxes do the things that you'd expect them to do. Comp swap is compare and swap. The value I give you, if the textile's value is equal to that, do the swap, else don't. UN versions of the same thing. And then the atomic counters. Now, the atomic counters you could think of is a small set of resources. Only thing you can do to them is increment them by 1, decrement them by 1, or read their value. And they are slightly different than what you think of with an atomic add of a -1. These would be get the value, return it back to my shader, increment the counter, and put that in the memory location. The decrement, however, is get the value out of the counter, decrement it, and return that value to the shader. And this is because what we effectively design these things to be used for is I'm using them as a way of getting a unique memory address, a unique offset into a texture buffer for each one of the fragments in flight. And as I'm running up the stack, I want to get the value that was there. And when I go and try to consume it, I want to get back down to the stuff that has been written, not the one that would be written. At the top of the stack, you've got something that's an empty value. So we decrement it, then return the value to you in the shader. So we also have some controls to help you, because we really don't want to shade if possible. And there's a lot of times where we can avoid that. Modern computer graphics with the depth buffers do a wonderful job of avoiding a lot of computation. In the past, with GLSL, if you wrote frag depth, we had to be really conservative. And we had to assume you could be writing any value at all there. This set of controls gives the compiler a hint and the driver a hint that you don't have to be that conservative. The first one, depth unchanged. Now, it's not that you're promising Knight to write the frag depth, because clearly you are writing the frag depth. The best way I think about this is I'm promising that the result of the depth test, the comparison with the fixed function depth, will be the same sense, true or false, to the sense of the depth test against the changed value. So I'm going to allow me to change the value, but I'm going to promise you that the result of the depth test will be the same. If you lie to me, you're going to get some really interesting undefined results. Same thing with greater than and less than, is you're telling you that you're either going to displace the fragment farther away or closer. And then we'll use the sense of the depth test to know when we can do the optimization of doing earlier depth testing. Now, earlier depth testing, even with these hints, will still get disabled if you have side effects in your shader. The side effects are atomic counters and image load stores. So we have a new one that says, basically, do early depth test, period, exclamation point, and that's layout early fragment test in. The depth test will take place prior to the shader. What also the implication of that is, if you do bother to write in your shader frag depth, that gets written to the bit bucket. You never see that depth again. So, don't try this at home. We are what you'll call experts. Mythbusters moment. I don't think even experts would do this, all right? But let's take a quick look at what this thing is doing. Layout early fragment tests in. So it's a fragment shader. Layout binding equals 0, offset equals 0. Okay, that's just telling you where the counter is going to be stored. Uniform atomic uint, a counter. Void main, atomic counter increment counter. Now quickly, what the hell is this thing doing? Go.
It's just incrementing the counter atomically. Is that what happens, fragment or vertex?
It's a fragment.
So can you count how many fragments the fragment shader ran on?
It's effectively an occlusion query.
Yeah.
Yeah, that's exactly all it's doing. Now, we have perfectly good fixed function that will do this for you. Use it. However, that perfectly good fixed function that will do that is restricted to doing one occlusion query in flight. So maybe if you need more than one for some strange reason, consider this. It's also possible if you have a more complex fragment shader, hey, got a little bit of extra time to do and increment this counter, go ahead, we're not even going to notice. But don't do a fragment shader that the only thing it's doing is incrementing this counter. Use the fixed function. So something old school, layout triangles in. So layout triangles in, we know this has to be a geometry shader. Layout points, max vertices equals 1 out. Okay, it's going to emit at least one, at most one point. I have a function bool classify triangle, function void emit hit, and my geometry shader is if classify triangle emit hit. Okay, what is this doing? Anyone? It's from way back machine in GL. It's in chapter 5 of the GL. Go ahead.
Picking?
It's selection. Yes, it's a picking. It's going to give you an unordered list of all the triangles that happen to hit some hit volume. If you use the transform feedback buffer, that's where they'll end up showing up rather than back in your memory. This can be actually something that might be smart to do. The one disadvantage, if you've got triangles, of course, you can end up with this. Bartol, can you give me a hand? So, right? Everybody's in front and behind everybody else, right? So the one problem with old school selection is thank you. Now we give him a hand. The one problem with that is that it's kind of ambiguous what the user wants, but your typical selection algorithms always would let the user toggle through. No, not that one, not that one, not that one, not that one! until you finally got to the one that was highlighted that you wanted. Something new school. What if we did selection on a per fragment level? Why not? This is what the side effects give us. So it's based on an example from JEC. Some wonderful colleagues at AMD came up with this great paper, OIT and indirect illumination using some other API. Good paper though. So the basic bottom line here is everybody gets really terrified of these big frame buffers with these big linked lists on them. Well, the nice thing about selection is usually you're looking at a little area someplace on the screen. 4x4, even if it's 8x8, that's not very much. So don't be so scared about it. It's not that much memory we're talking about. So we're going to create a selection size offset image. My example is showing you a 4x4. We're going to bind a head offset and a data store images. We're storing both where the pointer to the head of the pixel on that pixel is, and the data store for the actual records. We're going to bind a counter buffer, initialize the head offset and counter buffers, set up the scissor, disable depth buffering, no frame buffer output, render, and voila, we'll end up with a shader that does only side effects. So our head offset buffer is the one on the your screen, your left, screen right, and the data store buffer is the one that's going to store link, ID, and depth, and probably color as well. So the first triangle comes in, you just do a simple transform of that triangle from frag chord into the offset buffer coordinate system. You find out that it's going to hit the 2.2 texel. You read the value that was at the 2.2 texel, which was -1. You stick that in the link value. -1 is just a special value that says there are no more fragments here. You write out its ID, you write out its depth, and you update the offset buffer with the value of where you wrote the last fragment record, and that's currently 0. Next triangle comes in, it's the green one, you do the same sort of process for there. The cyan one comes in. Now this is going to be writing 3 pixels, quote unquote, simultaneously, right? We don't know what order they're going to be written, but we do know they're going to be written. So don't be sweating this, that on one implementation of OpenGL, those 3 might be pointers in order 2, 3, 4. Another one might be 2, 4, 3. Another one might be 3, 4, 2. There's all kinds of different rotations of that. Doesn't matter. It's going to go into the data store. It's going to go into the linked list. Each one of the individual fragments will be pointing to the right record. You keep on going and just live with the fact that you don't need to be certain about where every record that you've ever written actually lies in this image buffer. And then the final one actually happens to finally hit a pixel the second time around. And so now we're going to write down that's going to be the f-1th fragment that we've written. That will point back to the 0th record, and then the -1 tells me there are no more pixels left in that one. The shader is fairly straightforward. Layout, binding equals 0, offset equals 0. Again, we're just telling you where this counter lives. Uniform atomic UN, fragment counter. We're going to have one buffer, which is the UImage 2D. It's going to be 32-bit unsigned integers. We're going to restrict it, because this is the only thing that's going to be there, and we're going to make it coherent to make sure that every other fragment sees the same ones, because I have to make sure that the other fragments that are coming behind me don't get the wrong value there. One note, I'll back up for a second. I initialized my offset buffer to all -1s. I'm using an unsigned buffer. -1s were short for F and bunch of F's. So couldn't write all the F's in there, and so just -1, F, 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 each one of those things. It's just there's magic values, they no more pixels. Then the second one is just a long UImage buffer. I'm using a UImage buffer because texture buffer objects can actually be quite large. This thing I probably will never actually need to be able to use a large buffer, but I don't want to tell you you can't use one, so I don't want to be misquoted like Bill Gates is that like 640K will always be enough. There's still going to be a limit, but that's a hardware limit right now, but it is probably for this particular implementation of this algorithm, more than enough there. Function to transform the coordinates from frag chord into the buffer coordinate system, a function to pack the data, And so all we're going to do is a new offset, previous offset. The new offset will be done with an atomic counter increment on the fragment counter. Previous offset will exchange with the atomic exchange from the head offset buffer at that coordinate and put in the new offset. And then we'll update the image store at the new offset location and pack in the data of the previous offset plus the data like depth, color, and index. And voila, you've built yourself this wonderful linked list of every pixel that ended up going into that screen. One advantage here is this buffer only needs to be sized such that it has to store the average depth complexity of the scene rather than the max depth complexity of the scene. It has some nice coherent, not coherent, the way the memory accesses happen to be hitting that linear buffer, the texture buffer, ends up being quite nice on the rendering side. However, it scatters itself all over the place on the post-processing side, and I'm not showing you that. So that's about all there is there for me today. I want to thank you a lot. I also want to point you off to blogs.amd.com/developer. Our beta drivers are out on the website live as we speak. Thank you very much.